Okay, in today's video, I'm going to go over a very important story about the normal force, the elevator, and the second law. And of course, by the second law, we mean Newton's second law. All right, I'm going to go through 4 different situations, and in each case, the goal is to figure out what is the normal force. So here we have a person. The person is in an elevator. The elevator is suspended by a cable, and of course the person brought with them a bathroom scale. So this pink thing is here what is a bathroom scale, and the bathroom scale is going to tell us what the normal force is. The force of gravity pulls you down towards Earth. The floor pushes back up on you so that you don't fall through the elevator, and that is the normal force, and the reading on the scale is basically the normal force. Okay? So let's see what we get when we figure out what the normal force is in each of these 4 cases. Over here I have this blue arrow. The blue arrow simply tells us that up is in the positive direction. The arrow is not the velocity vector or the acceleration vector or the motion vector or a force vector. It just tells us that up is in the positive direction. Okay, so let's go through these 4 cases. Okay, we have the first one is the elevator is at rest. You have gotten in the elevator. You're staying there in the elevator, it's at rest, so therefore the important thing in this case is that the acceleration is equal to 0 meters per second squared. Alright, we're not moving. So therefore, we're going to draw the forces. One of the first things you always do on these is draw the forces. The downward force is gravity. We could put Fw, force weight, or Fg for force of gravity, but usually it's designated mg for the mass times acceleration due to gravity, and that is how you calculate your weight, which is a force. And then we have the normal force pushes up because we know we're not falling through the floor of the elevator. Alright, so those are the only 2 forces, and now we can apply Newton's second law and sum up the forces, because Newton's law says that the sum of the forces is equal to the mass times the acceleration. We just said that the acceleration is 0, so 0 times the mass is 0, and that tells us that the sum of the forces in this case is going to be equal to 0. And that should make sense because when you're at rest, your forces are balanced and the net force acting on you is 0. So let's sum up the forces. The normal force we're going to write down first. It's in the positive direction. We're going to put the force of the weight is second, and we're going to put a minus sign in front of it because it's acting in the negative direction, and then we're going to put 0 because those are equal to 0. And you can see that the normal force, the force that the floor pushes back up on you, is equal to your weight, and that should make sense. When you're standing still and you're standing on a scale, the scale reads your weight. So in this case, the scale is reading your true weight. Okay, let's go on to the next one. In this case, now we are speeding up. You've closed the door, the doors have closed, you push the button, the elevator starts to move up, and because it's moving up from a velocity of 0, we know now that when it's speeding up, that it is accelerating. So in this case, we do have an acceleration, and I'm going to put down here that the acceleration is not 0 meters per second squared. All right, now in which way are you accelerating? Well, you're moving up and you're speeding up, and it's important to notice that therefore you are accelerating in the positive direction. So it's good to write that arrow. That's your acceleration vector. It's pointing upwards in the same direction as your motion. Okay, so now we're going to draw the forces again. Let's draw the forces. We have the force of weight, your weight force, which is mg, and because you're not falling through the floor again, there is of course again the normal force, which we designate Fn, and now we can sum up the forces because those are the only 2 forces that are acting on you, and once again the sum of the forces is equal to the mass times the acceleration. Now the acceleration is not 0, so we're going to leave it just like that. Some of the forces is ma. Let's sum up the forces. We have the normal force, right, the positive force first. Mg points in the negative direction downwards, and therefore that is then equal to a positive mg. So I'm going to put down here for emphasis that this is plus a positive ma. Okay, now then once again let's solve for the normal force. The normal force is therefore going to be equal to mg plus ma. Oopsie daisy. Plus ma. Alright, now you can see when we're going upwards and we're speeding up that the normal force is going to be greater than your weight. It's going to be your weight plus the mass times the acceleration. And you should maybe have felt that when you're in an elevator and it starts to move, you kind of have to keep your legs straight because there's a force pushing up that's greater than your weight. Okay, so in this case, the normal force is greater than your weight when you're accelerating upwards. Okay, let's go on to the next case. Now we're in the elevator. We have stopped accelerating, but we're still moving upwards. We're moving up to the floor that we're coming up to, but we're moving at a constant velocity. And once again, when you're moving at a constant velocity, if your velocity is constant, then you are not, then you have an acceleration that is 0. So you're not accelerating. So once again, the acceleration is 0 meters per second squared. Okay? Now once again, we're going to draw the forces. We have the force pointing down is once again your weight, mg. And you have the force upwards because you're not falling through the floor is Fn, and those are the only two forces. And now once again we can apply Newton's second law. Newton's second law says that the sum of the forces is equal to the mass times the acceleration. The acceleration is 0, so once again the sum of the forces is equal to 0, and that should make sense because you're moving at a constant velocity. Your velocity is not changing. Your net force has to be 0. Let's add up the forces again, and you get Fn in the positive direction, and you get mg in the negative direction, and those are equal to 0. And once again, just like when we were at rest, Fn, the normal force, is equal to mg, and the scale has come back to reading your true weight or your weight when you're at rest, because now you're moving at a constant velocity, and just like when you're at rest, you are not accelerating. All right, so now the normal force is equal to mg. Okay, let's go on to the last one. Now you're coming up to your floor. You're getting ready to get out of the elevator, but the elevator is slowing down. So when the elevator is slowing down, it means your velocity is changing, and therefore your acceleration once again is not 0 meters per second squared. And we can figure out that if we're going upwards, but we're slowing down, that means our acceleration is in the direction opposite our motion, opposite our velocity, and therefore the acceleration points downwards, and we have a negative acceleration. We would have a positive velocity, a negative acceleration, and therefore we're slowing down. Okay, now we're going to draw the forces. Here's mg. We're not falling through the floor again, so we have Fn. And those are the only two forces again, and now we can sum up the forces. And of course, Newton's second law still says that Fn, the sum of the forces, is equal to the mass times the acceleration. The acceleration is not 0, so we're going to leave it like that. And we can sum up the forces. We have the normal force, Fn. We have mg in the negative direction, and therefore we put down that that is equal to ma, but we have to remember that the acceleration is negative, so it's negative ma. So this is kind of a conceptual thing you have to remember. You got to remember to put the negative sign in there because you are accelerating in the negative direction. So when we solve for Fn, for the normal force, therefore we get that the normal force is equal to mg. In this case, it's mg minus ma. Remember when we were moving up and speeding up, it was Fn equals mg plus ma, but now we're slowing down, and the scale is going to read less than our true weight, or less than our weight when we're at rest, by a factor of minus ma. Okay, so those are the 4 cases. I think that's a good exercise to make sure that you know how to use Newton's second law, to make sure you use the sign conventions correctly for your acceleration and your motion and the forces, and to put all that together, and you can see how the normal force will change based on the motion. Okay, so I made this final slide just to sum everything up. In slide 1, we said we were at rest, there's no acceleration, and the normal force is equal to our weight. When we're moving up and speeding up, we are accelerating, and Fn was equal to mg plus ma. Then we were between floors, we're moving at constant velocity, no acceleration, and once again the normal force is equal to our weight. And then finally we were slowing down, which means we were accelerating, we had an acceleration, but in this case Fn was equal to mg minus ma, so the scale would read less than our true weight. Alright, so I think that sums it up pretty good. Thanks for watching, hope that was helpful, and we will see you next time.